Hello, everybody. We are the Open Leg Bionics team, and we're excited to present to you all of our work for the past 2 semesters. Members of our team, we have Warren, Matthew, Connolly, Justin, Polani, and my name is Andy. So there are approximately 185,000 annual lower leg amputations in just the United States each year, and most of these amputees use passive prostheses that aid in walking, but only supply limited functionality. Now, powered prostheses have the potential to address these limitations, but unfortunately, they remain very expensive and are very inaccessible for users. So now Polani is going to talk about our main objective of our project.
Yeah, so as alluded to by Andy, the goal and objective of our project was to make powered prostheses more accessible. And to accomplish this goal, we made a powered prosthesis from 3D printed parts, a hand drill, and a bunch of other readily accessible components. So while creating a fully functional kind of market-ready product didn't seem like a super realistic objective, the main goal was more to set the groundwork for others to continue to build upon and ultimately creating a platform for future research, development, and accessibility in the assistive technology field.
So as far as our design specifications go, we were hoping to meet a couple of target values in a few categories. The first one is weight. We were hoping to stay below 3.5 kilograms, which is around 7.5 pounds. And this is because we were hoping to avoid making the prosthesis like unnecessarily cumbersome for budding engineers and for amputees to potentially use in the future, maybe. As far as cost goes, the actual cost to make the leg, we were hoping to stay below $1,500. As far as weight capacity goes, we were hoping to stay to stay above 75 kilograms, which is around 165 pounds. And this is because the worldwide adult male average body weight is 137 pounds or 62 kilograms. As far as torque capacity goes, we wanted to be above 20 Newton meters. And that's because for walking, it's 40 Newton meters, but we weren't necessarily expecting anyone to walk on it yet. And then for energy loss per cycle, this has to do with the battery, we wanted to stay below 50 joules.
So our design as a whole incorporated a lot of parts from the Makita brushless drill. So we took out the motor as well as the gearbox from the drill, and then we were also using the motor control ESC. We then put these parts into a 3D printed housing exoskeleton that was split into 2 halves in order to allow for manufacturability. The exoskeleton, being 3D printed, also allowed us to aesthetically make it look more like a leg, which is really great since we wanted it to be something that would look good if a user were to actually be wearing it eventually. We then used 2 aluminum shafts and as well as a 2-stage drivetrain system with 4-to-1 gear reductions. And chain and sprockets in order to transmit the torque from our motor into the knee joint. And then all of these were then sandwiched with all of our electronics, which Justin can lead into.
So embedded system and controls design was really challenging, but it was also kind of rewarding. Along the way, we modeled our system and we found that we needed sensors in multiple places. So we have incremental encoder at the motor shaft and we have an absolute encoder at the knee shaft. This allows us to compensate for the backlash in the mechanical system, and also it gives us a 400 times resolution on velocity. Through the modeling, we were also able to determine that we needed an IMU to determine orientation and position of the leg in space, and we also needed a ground force reaction sensor to determine gait cycle. The ground force reaction sensor, we had to build a custom one because typical load cells are very expensive in industry. And through a lot of prototyping and testing, we determined that the use of Hall effects and rubber was the best and most reliable method. We ran into a couple of challenges with like hysteresis of the rubber and like degradation and tightness of the, the cell itself. With all these sensors, we had to consolidate them onto one single motherboard. This is where we also located all of our processing power and memory. And that was our electrical design. It came together pretty well at the end.
Yeah, and obviously because of the new shell kind of design and just kind of the difficult, tedious nature of kind of taking that apart and accessing the microcontroller, we worked pretty hard to utilize the Wi-Fi capability in the Leg's Raspberry Pi as an access point and allowing for easy pairing with another microcontroller or computer. And kind of through this like server-client relationship that we made, we were able to streamline this process and wirelessly transmit and automatically upload new code as well as receive live data from the Leg. So going forward, that'll be a huge help on just updating code so the user, depending on their technical level, doesn't have to take things apart. It'll just be more wireless through their computer with the press of a button.
As far as the actual values for what we were able to meet in regards to our design specifications, you can see in our design specifications table where we were able to hit them. As far as weight goes, we were able to stay below our target weight at 3.4 kilograms, and we were also able to stay on budget as far as the cost to build it. Our weight capacity is a lot higher than the average weight of an adult male, and as far as torque capacity goes, we were able to stay well above the 20 Newton meters and even achieve potentially walking torque. And then as far as the battery goes, energy loss per cycle, we were also stay well below the 50 joules. And my other teammates will talk a little more about how we were able to determine those numbers.
Okay, so yeah, now getting into our energy analysis. First off, what we did with our leg is we estimated through dynamic modeling of our gear system or our drivetrain. In MATLAB, we used to determine the energy expenditure of the battery throughout one gate cycle. And from one gate cycle, we used to approximate the amount of steps until the battery lost power. So we started out last semester by choosing 3 theoretical gear ratios that are most reasonable for the size, weight, and price, and came down to gear ratios of 2-to-1, 4-to-1, and 3.2-to-1. So basically by understanding the inertial and dampening effects of our leg and making assumptions and understanding the biomechanics of the knee while walking, we can determine the power produced by the system and torque by the motor to find the energy expended by the battery during one gate cycle. And we use that to determine which gear ratio was the most efficient for our system. So in the bottom left, we see 2 specific plots that help us visualize the motor's characteristics. So in the left plot, we can see the root mean squared values of the vertical line. And you can determine whether the motor can handle the average torque requirements for the leg to perform one gate cycle. So you can see all the curved blue lines are the torque versus velocity profiles for the motor during one gate cycle. So it's like its path. And on the right side, we can see a power versus time plot. And by taking the integral of the total power, this gives us an estimated amount of energy expended per cycle, which we can then relate to the capacity of the battery to determine the total amount of steps. So finally, we found with our approximations that a 4-to-1 ratio lies within the range of torque speed curve and approximated the most amount of steps. So we acknowledged these findings that the 4-to-1 gear ratio was the most efficient, and we proceeded forward with that gear ratio. Our hope was that we would be able to use motion capture, inertial measurement sensors, and analysis for the leg's movement while walking, but those hopes came to an end for our project due to the pandemic and not having access to equipment in the lab. We were also hopeful in being able to estimate real-time energy expenditure of the battery with the use of force plates and analyzing the gate through one gate cycle. But instead, we estimated the dynamic model even further to get a better understanding of the newest prototype and how it might perform. So after spring break, by using the same methods as I talked about previously and taking new measurements of the parts in the leg that had changed over time, such as the mass of the knee connector, the shafts, and the overall mass of the leg, we were able to estimate that our current prototype here now has an energy loss of about 23.25 joules per cycle, which relates to a potential withstanding of 5,572 total steps. So now Warren will talk about the FEA of the external frame and the knee joint shaft.
So as for the structural design, to fill anybody who didn't see our projects last semester, it was an internal frame and everything was housed on the outside, the sprockets, the motor, the gears, and the chains were all housed on the outside, which served its function and we were able to use it for walking and testing purposes, but we decided that there were too many pinch points and it wouldn't be safe for the user to have that on their leg, and it was prone to damage and all other sorts of problems. So this semester we redesigned it into an exoskeleton so we could increase the second moment of area to make it stiffer while still using the same amount of material. It also helped create more space for our sensors and easier pathways for wires and electronics. As for the strength of our frame, we modeled it in FEA using ANSYS, and we had a safety factor of 5.3 when treating it as solid plastic, which the frame currently is 100% infill plastic. As for the knee joint, we also used 3D printed material and we printed it at 100% infill, but a change from last semester was to add aluminum shafts to help the standing load so that the plastic wouldn't be overstressed during our gait cycle. We ran into a lot of limitations coming into this design of the leg. The drill motor has a very specific position that it needs to be in, or it needs to be aligned very properly for it to work. So with this new frame, we struggled with alignment issues, and without the access to our own 3D printers, we weren't able to fix that solution. So we did not get a chance to test it out on this frame fully with weight on it, but we were able to get all the components assembled and slack out of the chain and improve it from the last semester's design. We have the leg right here if you would want to see it. So I don't know if you guys are able to see this. We can take. Did I just mute? Okay. We can take this off of the screen share. Stop share. And you guys can see this is the frame that we have currently. So we have full articulation going in, and there's only one pinch point where the knee would be coming into the end stops. But compared to last semester's, there's a major improvement. We could open this up, but you can see from the PowerPoint that the assembly of all the gears on the inside. We also have some more videos if you want to see the leg walking, which I can pull up right now. Uh-oh. Okay. My bad. Okay. 1 second here. All right, so this would be the previous generation of the leg. Is everybody able to see this? Give me a thumbs up.
Yeah.
Yeah, okay. So this is the previous design. You can see that the chains are exposed and it's a lot more hazardous than what we have this semester, and is not nearly as pretty as this new one.
Or sturdy.
Or sturdy, yeah. So that was that, and then we have another video which would be up close, so you can see the inner mechanics.
Yes, that would be the video we're trying to go for.
Go back up.
Needs gravity.
That's just showing it on a basic test bench with it just showing actuation of the motor and all of the electronics. So that was on our previous prototype, and it just demonstrates our electronics do work. And we are just needing to translate that into the new exoskeleton, which we would love to have done, but unfortunately with limitations to access the 3D printers, that was, as people have said before, that was a little difficult. Alrighty, I'll go back to the poster here, maybe. Okay, is that better?
Yep.
Awesome.
Unless anyone has anything else to add, I think we're good for questions.